I want to thank the organizers for giving me this opportunity to give this talk as well as visit the GGI as of my first time here. So I'll be talking about time dependence in AdS3 CFT2. It's a little bit off from the main topics of this workshop, but hopefully it's sort of reasonably interesting for most of you here. So it's based on a work I've been doing for a year and current work also with Surbi, who's a student of mine at Bangalore, and S. Prem Kumar, who is at Swansea. Of course, everybody knows that the study of time-dependent phenomena is an important question. In string theory, it is important to understand black hole formation, thermalization, and hopefully I'll convince you that AdS3 CFT2 holography is sort of a good testing ground for studying this time-dependent behavior. One of the simplest questions people study is that they inject energy at t is equal to 0 or a time span delta t, and observe how the system thermalizes and form a black hole in the bulk. But this question is quite difficult to address, and usually the approximation which is done is that you assume a black hole forms and study how various other probes like the 2-point function relaxes to thermal equilibrium. And studies of this kind related to AdS Vaidya collapse have been done by such authors recently. They address this question in CFT2. But I will be studying a more simpler question, and hopefully it is also of interest, and it does teach us something. So the simpler question is basically to consider a geometry of a massive particle falling into the black hole. And of course, it's a time-dependent geometry if you take into account of the back reaction, and then and study time-dependent probes, behavior of time-dependent probes in this background. Now, of course, this simpler question does not address the fundamental aspects of black hole thermalization and so on, but hopefully it's an interesting enough, as you will see, hopefully it's an interesting enough question. And what we will basically discuss is the behavior, we'll focus on the behavior of entanglement entropy as a probe. And our aim would be to study universal features of the time dependence. And therefore, hopefully this universal features will be seen in the bulk. Yes? Yeah, very massive. It's the dimension is like order C. So we will, when we study it in the bulk. So in the CFT, I have more general treatment. So we'll examine the time dependence also when the CFT is held at finite chemical, higher spin chemical potential, and we'll study the system in the bulk when this infalling particle has higher spin charge. Okay, so let me start with the CFT setup. Okay. So this will be the bulk of the talk, basically. So what we will do is consider localized excitation. The excitation is of width epsilon, and in the 2D CFT, held at finite temperature. It's released at x equals 0, t is equal to 0, and therefore, since it's a conformal field theory, it will spread on a light cone. And the excitation is created by a primary of operator O, delta dimension delta. And what we will examine is the change in entanglement entropy of an interval L1, L2. This interval is called A, as this pulse travels and enters into this interval. So of course, this is a time-dependent question. And I'll just state the result, roughly the result, and then we will work towards it. The result, so when the width is really small, when the width is 0, basically there is a bump. And this bump is in this dotted lines. It's given in this dotted line. And it was evaluated earlier by Tadashi and collaborators, actually. But there is a correction when the width is finite. In fact, here is the plot. This blue plot is when the width is finite in a definite CFT. It's actually the minimal model CFT. When the width is finite, the profile is of this kind. And what we will do is basically evaluate the epsilon squared correction, the width squared correction to it. And we will show that the width squared correction is universal. And it sort of corrects this bump, this step function bump of this kind to this particular feature, this red feature. Okay. So this is what I've explained. epsilon is equal to 0. The dashed line was actually found by these authors, and this jump is also related to the operator. It's called the this quantum dimension is related to the characteristics of the operator. We will come to it. And the general shape of the curve, of course, the way it sort of smoothens out depends on the details of the CFT. But this growth is independent, and in fact it is independent of central charge even, and we will show that it's universal. Okay, so that's the sort of rough result. So the details. So how do you set up this question? Is basically first you write down the density matrix. Here's the density matrix. So this one is basically the thermal density matrix, and here is the operator insertion which creates the particular state. The state is smeared over epsilon by this particular Hamiltonian. In fact, by imaginary evolution, this state is smeared, and then it's evolved in time t. Okay, so in fact, this evolution can be thought of as insertion of the operator at complex times like this, and then it's evolved. And the coordinates we will discuss are basically in Lorentzian signature, light cone signature of this kind. For instance, so let's see if this density matrix corresponds to the state we are interested in. Basically, this pulse traveling on the light cone. So what you do to check that is basically evaluate the stress tensor in that particular density matrix. Here it is, and in fact, you can translate it from this particular definition to a correlator. In fact, it's a 3-point function of the stress tensor inserted at x minus t and x plus t. You can see how the insertion operator acquires the time, the evolution time dependence, which I evolved here. And this is the normalization basically. Okay, and this is an easy correlator to evaluate. In fact, it's just stress tensor with two primaries, and you can evaluate it, and you can see this is the formula. Okay, and in fact you have to translate it to the cylinder, and if you plot this particular function, you can see some kind of Lorentzian kind of structure here. So if you plot this particular function, you'll see that at t is equal to 0, it's a bump, and then it splits. The bump splits and it travels on the light cone. You can actually see it in 3D if you want to see, but here I've plotted at 0.05, and you see it's at 0.05. And so this pulse travels and it moves into the entangling interval, and we are asking the question, how does it change the entanglement entropy? Yes? Here, the line is infinite, yes. No, it's not a torus. This is an infinite line, but at finite temperature, so it's cylinder. So, to evaluate entanglement entropy, so we use, of course, the replica trick for the reduced density matrix, and in path integral basically translates to a path integral of the cylinder with a branch cut at these points, at the points of the interval. And there is an insertion of the operator at these imaginary times. Here is the particular sort of structure of the branch cut cylinder. Here's the beta and the insertions of the operator, and I have not drawn it well, but this is the branch cut x2 to x3, and these are the light cone coordinates of that x2 and x3, and of course these sheets are joined together at the branch cut over and over again n times. Okay. At every sheet, every sheet there is this insertion of these operators. Okay, so basically on the n-fold cover of the cylinder, this evaluation of the trace of the density matrix translates to evaluation of the 2 endpoint function on this branched cylinder. Okay, so we'll have to evaluate the 2 endpoint correlator on the branched cylinder. Now, of course, that seems to be a hard task. Okay, so again, I have detailed the sort of setup. So there are these operators insertions, and at every copy of the cylinder, there are these O and O dagger insertions, and the branch points are located at this points. So they're separated by distance, spatial distance L1, L2 minus L1. Now, the Rene entropy is basically given by the change in the Rene entropy is basically given by the insertion, the density matrix with the insertions, 2n insertions, divided by the usual density matrix on the branch cylinder. Now, to evaluate this 2n point function, you go to the covering space. You go to this, you use this uniformization map, which takes this branch cylinder to a plane in which each copy of the branch cylinder is basically a wedge of 2 pi by n. Okay, width 2 pi by n. So here's the map. Here's the map. It's sort of, you can understand it if you stare at it for a while. Basically, it takes the cylinder to this wedge. This 1 by n takes into account for that. So, and if you look at it, if you track the insertions of the operator in time, okay, this is how it behaves. So it's sort of, so you can see here are the insertions of the operator here. It's on a wedge, okay, and here are these insertions, okay. So this is like I epsilon and minus I epsilon, and so on, repeated onwards. The key point to understand is that as when the time changes, actually, this insertion changes in a particular way. And what happens is that when the time is such that it enters the interval, then this W1, which is very close to W4, they were 2i epsilon separated, they sort of, the W1 approaches W4 in the adjacent copy. So let me emphasize that again. So basically, the key point is that when the time enters this interval L1 to L2, the operators approach the adjacent wedges, and this is only in the holomorphic side, actually. So the way to see it is the following: evaluate the particular cross ratio, and you see, and the epsilon is going to 0. Epsilon was the width, and you see that there is a change in sign when t is between L1 and L2, and because of the change in sign, okay, this flips, and therefore the nth roots basically pick up a phase 2 pi by n, and that sort of rotates the holomorphic side such that the sort of it moves close. W1 moves close to the adjacent branch. Okay. While the anti-holomorphic thing remains the same, there is no change in sign in that, and the anti-holomorphic coordinates remain the same. So this is the key point to realize that. So maybe I can sort of mention it in an n equals 2 setup. So here is W1, W4, and here's the copy, W1 and W4 copy. And initially it was like this together, and then after the time in between time L2 to L1, this thing appears closer. So there's sort of a flip in that. So here again I have written that this thing, what's the phenomena, and the next step is, because epsilon is approaching very close, you can actually evaluate the 2n point function by using the operator product expansion of this O and O dagger. And say we assume that the conformal dimensions of the theory, or the lowest lying conformal dimensions primary, are greater than 1. Okay, so just assume that. And then what is important is basically the stress tensor which appears in the OPE. Okay, and if you want to approximate this 2n point function by its OPE, then all we have to do is basically evaluate the expectation value of the stress tensor on the branch cylinder. Okay, so this 2n point function, each of them we take epsilon close by, and we have to evaluate the expectation value, and then so all you have to do is basically expectation value of the cylinder of the stress tensor on the cylinder, branch cylinder. And that also can be done using the uniformization map. So, what happens is that because of this flip here, this flip in the holomorphic side, at every time it flips, we have to use this fusion transformations when we sort of flip the branches. We have to use the fusion transformation and let the fusion transformation be FOO. And putting all this together, we can approximate basically the 2-endpoint function. The 2-endpoint function essentially admits this particular expansion. Okay, and the epsilon is equal to 0 term is basically the step function. And the step function, this happens because, as I said, when the branch flips, there is a fusion coefficient, and basically you'll have to take the log of that. And the epsilon squared term, we evaluate by evaluating the expectation value of the stress tensor on the branch cylinder, and that leads to this. And essentially, this coefficient, this term which appears as epsilon squared term, is basically a Schwarzschian, which takes you from the branch cylinder to the uniformized plane. So that's that. Okay, and that has this very universal time dependence. And in fact, what appears here is just the coefficient of the dimension of the primary. It doesn't even have the central charge, and this whole thing is a universal time dependence. So let's write this result in a more general way. So here it is. This is the epsilon squared coefficient, and all you have to do is evaluate the expectation value of the stress tensor on the branched cylinder geometry. The branches are at these points, okay, and substitute that, and then you will basically get the time dependence. Okay, so, and as you can see that from this evaluation, this object is this time dependence is entirely universal. It just depends on the map, and also it's important to realize that this expansion, epsilon expansion, is an expansion when the times are not very close to the L1 and L2. So let's see this in slightly, let's have another more intuition about this term, and it also will lead us to certain checks. Okay, so if the time, if first we take one of the intervals to be infinite, okay, we take the intervals to be infinite size, and then we take large times. Then you'll see that okay, you basically can ignore the initial region, okay, and it's basically a branched. It's a cylinder, okay. It's just a cylinder branched n times. So its expectation value, it's just a cylinder with n beta periodicity. Okay, and it's basically so it's a stress tensor expectation value on the n beta periodicity, and then you can evaluate it. It's just this is the expectation of stress tensor on the cylinder, and then again we can take this. We get this static, the asymptotically static jump in the entanglement entropy of this kind. So this, of course, can be reproduced exactly from the time-dependent profile too. Okay. But there is an intuition to see how it becomes static and so on. So it sort of gives an alternative check. So let's see the checks we have done for this profile. So we have checked this analysis, this OPE analysis, which I mentioned, against a 4-point function correlator, in which we evaluate the 4-point function using conformal blocks. Okay? So at epsilon squared. Then we compare it against minimal model CFT. So in a minimal model CFT, especially in the second Rene entropy, okay, so this is a minimal model CFT, PP prime minimal model CFT. This is the formula for the central charge, and here is the primary which we'll focus on. And the 4-point function of these primaries are known. If you're looking at second Rene entropy, it's just a 4-point function, and the 4-point functions of these operators are known in terms of hypergeometric functions. And of course, so it's an exact result in epsilon. Okay, and you can evaluate epsilon squared and compare it against the OPE analysis, and of course it agrees. This is the quantum dimension, and here is the epsilon squared correction, and here we have plotted again. This is the quantum dimension jump, and here is the epsilon squared correction to it, okay, which gives you this profile of growth, and this is the exact result for the second Rene entropy in the minimal model. So this is the comparison. Again, I have zoomed in on this particular aspect. Yeah. Yes. Yeah. Then there's a correction there is a. Yeah. I have chosen the PP prime such that the one is above. Yeah. In fact, the next thing I said is that we have repeated it for the free fermion model, in which there is a U1 current which contributes to the epsilon squared. And of course, if you subtract that U1 contribution, you will get this answer. So that is a check. So let's go over to the higher spin deformed version of this calculation. So this is this is for any 2D CFT. So in the higher spin deformed version, so we consider the CFT with higher spin S chemical potential, and it's deformed in this particular holomorphic manner. Okay, and this deformation is introduced in each copy, because this is the deformation of the CFT. So it's in the calculations of Rene entropy. So this deformation is introduced in each copy, actually. Okay, and so here is the deformation in each of these ith copy. And what we have to do is basically calculate. Now the question is that, okay, we want to correct our calculation to say some mu squared order, perturbatively corrected. So we'll have to calculate these correlators along with this deformation. Okay. So for sufficiently small mu, in fact, this is just the scaling analysis. For every order in epsilon, there is a mu expansion, and then one can correct this, and there is this order epsilon squared, mu squared correction, and this is the leading term. Actually, we can show that this is the leading term, and we can even show that this is universal. So that's the next sort of calculation. So the time dependence, just like with exactly, you got to argue exactly the same way. So we have these operators close by, okay, O and O dagger close by, and now the CFT is deformed with higher spin chemical potential, and therefore perturbative analysis, conformal perturbation theory says that you got to bring, I mean, in the from the action, you got to bring down sort of these additive terms in W, and the correction basically turns out. When you use the OPE, it turns out that you have to evaluate the following correlator: stress tensor and W and W. So this is two insertions. The first insertion actually vanishes. You can see it from just the TW correlator. So it's only the second insertion, second time of second order perturbation theory which contributes at order mu squared. And of course, because it's a conformal perturbation theory, you have to integrate this, integrate the current over the cylinder. Okay. So this is the thing. So as seen from here itself, you can see that this is a correlator of currents, and therefore, since it's a correlator of currents, it's universal. Okay, and there's a correlator of currents on the branch cylinder, and you know, you have to do that integral, but the integrand is universal. Therefore, the integral also will be universal. And what we did was earlier on, various works, we developed the prescriptions for doing these integrals. And these prescriptions, there is a definite prescription or sort of ordering prescription for evaluating these integrals, and that was checked against various methods. Okay, it was checked against holography, in which we corrected the entanglement entropy. You know, we compared it against entanglement entropy of Wilson line. So it was checked against holography. It was also checked for the free energy, okay, against alternative perturbative methods developed by these authors and Matthias here. So that prescription sort of works. Okay, so we use that prescription. I mean, there are checks for that prescription to evaluate those integrals, and they're long. I mean, the integrals are long, and let me just write a formal expression for the epsilon squared mu squared correction, which is universal. Okay, it's basically this term, and you'll have to do this integrals. And I wouldn't show you the expression for the for that integral. It's in the paper, but let me plot it. Okay, so we have evaluated explicitly for spin 3 case, and let me just plot it. Though I am not showing the expression. So here is how it behaves at various beta. It's similar to the stress tensor insertion. There is this sort of various beta from top, the increasing values, okay, and it's similar to the stress tensor correction for this. And what are the and here just to show you that we have done the integral, we have taken the large time length interval, and here's the time dependence of that. That's considerably compact to sort of show. Okay. And as a check, so let's see the checks of this. Of course, it's a tedious calculation. A check for this calculation is that we have compared the mu squared epsilon squared term with the free fermion theory. The free fermion theory admits higher spin 3 deformation, and using the explicit calculation correlators, we can evaluate the second Rene entropy and compare it with the OP analysis. And now again, as we discussed, we have to subtract the U1 current contribution for this, and we check. Okay, and I said there is this geometric intuition we have. That if you take the length of the interval to be very large, okay, and afterwards we take the time to be large, basically it's a cylinder, n copies, it's a cylinder with n beta radius, okay. So these correlators go over to this correlator where n beta, it's n beta, of periodicity and thermal correlators of periodicity n beta, and we can evaluate this using conformal order entities from the 2-point function W. And of course, this explicit calculation using integrals and everything are compared against this limit, okay, which is independent, which is sort of independent. We just evaluate this directly. Here we go through the integral process, and they do agree, so that's sort of a check we have. And in fact, because of this fact that the correction at epsilon squared mu squared order is large times and large interval, a large interval and large time limit is basically this 3-point function. In fact, there is a very nice answer. This is the answer we get, okay, for the Rene entropy, and this of course can be generalized to arbitrary spins. And here's an answer for the arbitrary spin. Yes, here's an answer for the arbitrary spin. Well, it's an answer. Unfortunately, as you will see that we don't have a holographic checkup for this. I will come to it soon. So these are the two sort of CFT results we have. The universal correction at epsilon squared order for this time dependence. This time dependence, by the way, is called quantum quench, local quench, and the epsilon squared mu squared correction, which is also universal. Now let's see what we can check against the holography, okay, of this setup. So as I said, the holographic setup for this has been studied for some time actually. It's as I said, it's this infalling particle in the BTZ black hole. So the BTZ black hole is the thermal CFT, and this sort of this excitation spreading out is essentially an infalling particle of mass m, which is related to the dimension, and it falls from a distance epsilon from the boundary, and the entangling interval is located on the boundary. Okay. And this kind of time-dependent back-reacted geometry was initially, of course, in the early days of AdS3, Horowitz and Itzhaki discussed it, and it was brought back more in a more precise form by these authors recently. So let me just describe the setup. It's quite a complicated setup, and it's at least for me it was intuitively hard to understand. So what we do is basically consider a geodesic falling into the BTZ, okay, and the geodesic starts at distance epsilon, and the back-reacted suppose you have the particle at the origin, the back-reacted geometry is basically a conical defect. Okay, this is the metric of the conical defect. And here is this relation of the defect with the conformal dimension, so Newton's constant, radius of AdS3, and so on. Okay. So what we do is basically map the coordinates of the conical defect to the coordinates of the BTZ, using the fact that both can be embedded in R22. So map the conical defect into the BTZ coordinates, as such that when you do this embedding, the origin r is equal to 0 it basically translates into the trajectory of the geodesic of the infalling particle. So here is the map. Okay, you can see that is R22 by actually squaring this and squaring this and subtracting this part. It works out on the other side. So these are the coordinates of the conical defect, and here's the coordinates of the BTZ, x, time, and the radial coordinate z, m is the mass, which is related to the temperature. Okay, and you can see actually this r is equal to 0 when you put in this equation turns out to be the equation of the geodesic actually. And so we have sort of that trajectory to maps the r equals 0 point of the conical defect maps into this trajectory. And here I just given the metric of the BTZ in these coordinates, and this is the temperature related to this, and just you can convince. And this lambda is basically related to the epsilon. It's a boost. It's related to epsilon by this manner. And you can actually check, I'll just say it again, you can actually check the r is equal to 0 is basically the trajectory of this infalling particle. Okay. So this is the map, and once you have this map of the conical defect into the BTZ, you substitute for these coordinates, I mean the conical defect coordinates, the BTZ coordinates. So that's it. So substitute the map of the BTZ coordinates into the metric of the conical defect. That geometry is a very complicated geometry. It's a time-dependent geometry, and that's the candidate geometry for the local quench. So it's of course a complicated geometry. And so what are the tests done? So one test is just to evaluate the one-point function of the stress tensor, and that has been shown to agree with the CFT. So you remember that one of the first things we did with that density matrix was to evaluate the one-point function of the stress tensor, and that agreed. And this evaluating it in this geometry agrees. Okay, and what we will do is evaluate the entanglement entropy in this geometry, and we will use the Chern-Simons formulation so that we can generalize with the view to generalize to higher spin. Okay. So in the Chern-Simons formulation, basically we have these connections, left SL2 or right SL2. It can become SL3 for higher spin and so on. There are this flat connection part, and if you define these matrices of this kind, the Wilson line, which connects 2 points, which P and Q, which basically is the entanglement entropy, is given by this expression. Okay, and evaluating the Wilson line between 2 points, P and Q, basically with these particular coordinates, we can obtain the entanglement entropy. And here's the answer. It's sort of, it looks different. This is for the conical defect. And of course, we have to substitute the coordinates of the conical defect into the coordinates of the BTZ in this answer. And you can actually see that it roughly looks like the ones which you're familiar with. When delta t, when this spatial interval, the time interval is 0, it becomes like 1 minus cosine hyperbolic, which is like sine hyperbolic, and so on. Which is sort of familiar with people who know this. But here the time intervals are also important. And if you substitute this and look at the epsilon squared correction, we do indeed get the same answer. It's quite non-trivially appears. Okay. But this epsilon squared answer in gravity appears for t less than L1 and t less than greater than L2. Okay. In between, actually, we can't see the saturation to the quantum dimension. And the reason is basically effectively the quantum dimension. In between the thing, initially it actually develops logarithmically, but we can't see the saturation to quantum dimension because essentially the quantum dimension is very large, and because the conformal dimension is very large, and holographically it is not seen actually, at least for till now. We have to do, I think, 1/c corrections to see it. As I said before, we couldn't successfully set it to compute this mu squared epsilon squared correction. Essentially, the reason is because we could not find the backreatic geometry of a conical defect falling into higher spin black hole. So here, if the setup is such that the CFT is held at higher spin chemical potential, we need a backreacted geometry of this conical defect into falling into this thing, and that we could not do. But we do another thing. So for that, let me introduce another time-dependent quantity, which has been focus of interest recently, which is called the scrambling time. So I have 10 minutes. Yeah. So let me sort of introduce it briefly. I will. These are the topics of the current work, so I will not be so detailed, but you can ask me questions, and then I can hope to clarify. Okay. So this is a quantity of recent interest called scrambling time. So let me sort of describe you in the same setup. So essentially we have this BTZ black hole, eternal BTZ black hole. Okay, so here's the singularity. Say these are the boundaries. Okay, and we have the entangling intervals L2. Okay, and we have an entangling interval A, and we have an entangling interval in the other copy, in the other boundary. And what we see is that we send in an infalling particle. Okay, and we ask the question. Okay, we ask the question: when does the mutual information? Okay, the infalling particle is sent in, and there is a back-reacted time-dependent geometry in the Kruskal extension. And we ask the question: when does the mutual information go to 0? In the infalling particle is released in the past, and we calculate the time at which it is released when this mutual information vanishes. So that's the scrambling time. Here's a picture. Oh, okay, I didn't know the picture. Here's the picture of that particular thing. Here are the intervals. Okay, we compute the mutual information, and when the mutual information correlation is destroyed by this infalling particle, which is released at epsilon, is what is computed. And if yes, yeah. Yeah, it's sort of, what I meant was the slice. Slice there, but I just drew it this way. It's you just have to imagine there's an L1, L2 at the same time, L1 and L2 at the same time. Yeah. Yeah. So this is at the same place. Same. Yeah. I drew it. It was not drawn. And so if you calculate the mutual information, it's known. I mean, you can calculate it with the setup, with this infalling geometry, and you can calculate it, and it gives this particular formula. Okay, there is a dependence on the conformal dimension and everything, but basically there is a logarithm with respect to the central charge, and the coefficient in front of it is called the Lyapunov index. Okay, inverse of the Lyapunov index, and that dictates at least how certain correlators grow in time. It's called the out of time ordered correlators, and it controls chaos in these theories. Now, so there is a bound on this particular coefficient given by these authors. It's given in this expression. What we can do is we can repeat it when the infalling geometry particle is of higher spin charge. Okay, so essentially, you see, how did we create this infalling geometry? We created it by looking at the conical defect, okay, and then mapping the conical defect coordinates to the BTZ. And the map basically was determined by the geodesic equation. Now, when the infalling geometry has higher spin charge, but the BTZ black hole doesn't have any higher spin charge, the geodesic remains the same. Okay, it's blind because there's no charge and there's no interaction because of that. The geodesic remains the same, so we use the same map. Okay, we use the same map. So and we evaluate the Wilson lines using the the entanglement interval using the Wilson line prescription given by Debord and Jotard. So we do that, and we evaluate the scrambling time. Okay, and it changes to this particular order. It's in fact it violates the bound. And just as a check of the background, in fact, from the CFT you can predict that this coefficient is actually this epsilon cube Q charge coefficient vanishes, and that is true in this geometry. Actually, we have checked that just to be sure of the setup, and it's a weak check, but we did this check, and this Lyapunov index violates this bound, and it agrees with this recent calculation of Perlmutter of out of time ordered correlator. Here we are seeing it from this mutual information point of view, and the reason it was argued that reason is because somehow the boundary theory is not unitary, and just as several checks, We have repeated also the out-of-time ordered correlator in the bulk for the SL3 higher spin theory, and reproduced the fact that the Lyapunov index change violates the bound. And if the infalling geometry is not, if particle is not not charged, then there is no violation, in fact. And there's also agreement with the OTO calculations. Okay. So let me just summarize, and I'll end at that. So basically, we obtain universal features in time dependence of local quenches of 2D CFTs with and without higher spin chemical potential. And we have seen the violation of the Lyapunov index bound for the SL3 higher spin theories. And somehow that indicates, I think in the literature it has been said that finite truncation of higher spin theories is not unitary, and this is another indication of that fact. So I'll end it. Yes, yeah.
Maybe I missed something, but
Yeah.
suppose you have a higher spin black hole there,
Right.
and it looks like that you still use the geodesic motion concept for your computation for.
Yes, yes, yeah.
I don't think this is a consistent story actually to do, because
So we didn't use the computation of in a high spin black hole. We did not use the geodesic computation, but we use the geodesic computation when the black hole is BTZ and the infalling geometry is higher spin charge. So then I think there is no interaction. There is interaction between, because this does not have the higher spin charge, and so we use the geodesic computation. Yeah, and the other case is complicated. That's the reason we are not able to produce the epsilon squared, mu squared kind of corrections. Yeah, that's complicated setup actually.
Thanks.